Here's a question. In a sorted list, can you find where a target starts and where it ends? Take this one. In 5, 7, 7, 8, 8, 10, where does 8 begin and where does it stop? We want the range for 8, and the answer is indices 3 and 4, not the values 8 and 8. And if 6 is the target, we return -1, because 6 never appears at all. Pause for a second. What would you try first if you were doing this by hand? The obvious approach is, walk from left to right, remember the first 8, keep going, and update the last 8. That works on this example. But notice what happened, we still touched every number, even after the 8s were already found. Now scale that up to a huge sorted list. The sorting gave us structure, and this scan barely uses it. So even though the scan is simple, it grows with the whole array. The problem asks for O of log n, so we need a different move. Let's slow down here. In a sorted array, what information do we already have that the scan throws away? If the middle number is too small, the whole left side is too small. If it's too big, the whole right side is too big. So what are we really searching for? Not just any 8. We want the boundary where 8s begin, and the boundary where they end. And here's the move. Use binary search twice on this array, a train of compartments numbered in order, to find both boundaries. Same idea, said another way. One search keeps pushing left when it sees 8, and the other keeps pushing right. You might think one binary search is enough. Watch out. Finding an 8 does not tell you whether it's the first one or the last one. So the rule is, when we hit the target, we save that index, then keep searching toward the boundary we care about. Let's trace the left boundary first. Left is 0, right is 5, so the middle lands at index 2. Index 2 holds 7. 7 is smaller than 8, so the first 8 must be to the right. Now left is 3 and right is 5. Middle becomes 4, and index 4 holds 8. Good. We record 4, but we are hunting the first 8, so we keep searching left by moving right to 3. One more step. Left and right are both 3, middle is 3, and that is also 8. We record 3, then push left again. The search stops, and now we know the first position is 3. For the right boundary, we repeat the same search, but on a match we move the other way. That lands on 4. Notice what just happened. We never scanned through the whole block of numbers. Each step threw away half the remaining search space. Each search shrinks by halves, and we do it twice. The extra memory stays constant, so time is O of log n and space is O of 1. Let's write it. First, we make one helper for the first position, with left, right, and answer starting at -1. Inside the loop, smaller goes right, bigger goes left, and on a match we save middle and keep pushing left. The second helper is almost identical, except the match branch pushes right, so we can find the last position. Then we call both helpers and return the pair. And that's the pattern. One sorted array, 2 boundary searches, 1 clean answer.